So last time we talked about the extra element theorem, how it's used, and we went over a brief example. So this video is going to be a derivation for the extra element theorem. Where did it come from? How do we get it? So in general, if you have a two-port network like this, so you've got a certain input voltage, certain output voltage, and there's also your input and output currents. You can attach an extra element to it with an impedance Z, and you can find the transfer function of this new circuit, H nu, from the formula H of S, which is your old transfer function, times 1 plus Zn over Z, divided by 1 plus Zd over Z. And Zn and Zd are just your driving point impedances, both with your input shorted and your output set to 0. But where does that actually come from? So if we were just to write down an equation, we didn't know anything else, it would just be that V out is equal to H of S times Vn. Right, that's just the definition of the transfer function. So we're going to write it slightly differently and say that V out is equal to A1 times Vn. So the reason for this will become clear quite shortly. So if we say that associated with the extra element that we're adding, there's a certain voltage V and a certain current I. Actually, sorry, as we defined it, the current should be flowing in the opposite direction. So there's a certain voltage V and a certain current I. So we'd expect this equation to be modified somehow, and it turns out that we can just add an additional dependence. So this is a linear circuit, so we'd expect no matter how it's dependent on the extra element, we'd expect the output voltage to be linearly dependent on either the voltage across the element or the current. And we chose the current here because this is the parallel formulation, so this will turn out to be much more convenient. And we're going to write down a second equation, which is V, which is the voltage across our extra element, is equal to B1 times Vn plus B2 times I. And this is not so unreasonable. We're essentially just saying that the voltage across our element is dependent both on its current and on the input voltage. So we're just writing down two arbitrary linear equations, and these are going to let us solve for our new transfer function and derive the extra element theorem. So okay, so what are we ultimately trying to do? Well, we're trying to solve for V out over Vn, right? And we're trying to solve for V out over Vn with our new system of equations. So if we divide this first equation, if we divide the whole thing by Vn, we get that it's equal to A1 plus A2I over Vn. You're like, oh, okay, great, there's a Vn on the bottom, but we've got another one here, so we can solve for that. We say that, so rearranging this bottom equation, V minus I times B2 equals Vn, and we divide everything by B1. So we can plug that in here, and we say that V out over Vn is equal to A1 plus A2I over, and this is a little ugly, but V minus I B2 over B1. And we're done. That is the extra element theorem. Now, the trick is that realizing that this algebra can be rearranged into something meaningful. So that's the tricky part. So if we rearrange it, we can, so let's rewrite it here. So V out over Vn equals A1 plus A2, and if we bring the B1 up top, that's A2 B1I over V minus I B2. So, okay, let's get this all in one fraction, make it look a little prettier. So multiply A1 by V minus IB2 over V minus IB2. So A1 times V minus IB2 over V minus IB2 plus A2 B1I over V minus IB2. And rearranging a little further, we get A1 out front, which was our initial transfer function, times V minus IB2 plus A2 B1 I over A1. And the reason that I did that will become clear in a moment, divided by V minus IB2. Okay, so you'll notice that we've got a voltage dependence and we've got a current dependence, but we know our extra element has a certain impedance associated with it. So if we divide everything by the current, and this is the current through the extra element, then that I cancels, that I cancels, that I cancels, and we have V over I and V over I. So we can rewrite this like A1 times Z, which is our extra element's impedance, minus B2 plus A2 B1 over A1 divided by Z minus B2. Okay, cool. So now all we need to do is rearrange it in the form that the extra element theorem was originally presented in. So if we divide everything by Z, we get 1 minus, and I'm gonna multiply this B2 by A1 over A1, so it's 1 minus B2 A1 minus A2 B1 over A1 divided by 1 minus B2. Oh, and there's Z's here now. So all we need to prove is that negative B2 is nothing but the ZD, which is, if you remember, the impedance when the input is nulled. Well, if we go back to our original set of linear equations, we have V equals B1 times Vn plus B2 times I. So if we null Vn, if we set it equal to 0, we're left with V equals B2 times I, or V over I equals B2. Now, this V over I is it's referring to the current and the voltage across the extra element. If we're instead referring to the current that's going into the equivalent impedance, then we need to reverse the sign. So if we were to use Ohm's law, Z equals V over I, we just need to flip the sign of I. So V over I equals B2, or our corrected V over I equals negative B2. So that was with some messiness involving the sign. So okay, cool, that's correct. So with our input nulled, we get a value of negative B2, which is exactly what we wanted. Now what about this other slightly more complicated looking thing? Well, if we go back to our set of linear equations, this time we're setting V out equal to 0. So we're left with 0 equals A1 V in plus A2 times I, and V equals B1 V in plus B2I. And we can solve for V over I here. So if we say V1 or Vn equals minus A2 I over A1, just from this first equation, substitute that into the next one. V equals B1 times negative A2I over A1 plus B2I, or if we divide everything by I, V over I equals negative B1 A2 over A1 plus B2. Multiply this by A1 over A1, and we get negative B1 A2 plus B2 A1 over A1. And that is indeed the term that we are looking for. You'll notice there's again a flipping of the sign because we need to account for the fact that the current is flowing in the opposite direction. But this gives you the correct answer. So this is interpreted as Zn. It's the impedance that the extra element sees when looking into the rest of the two-port network when the output is nulled or set to 0. So that's the derivation for the parallel form of the extra element theorem. So